Hello, welcome to this lesson of Mastering Statistics. Here we're going to start to dive into the essential core concepts of statistics that you'll be using forever and ever as long as you study statistics. Here we're going to talk about random variables and discrete probability distributions. You read that title, it looks intimidating. It's not a variable, it's a random variable, and it's not just a probability, it's a discrete probability distribution. See, these words can scare the life out of a lot of students, and a lot of books are super hard to understand with what these things really mean. And you look at equations and formulas and lots of drawings, and then you can just go nuts. I'm going to make it very, very easy for you to understand. Just take a deep breath, realize that this is very simple. By the end of this lesson, you'll know exactly what a probability distribution is, what makes it discrete, what a random variable is, and how it is different from a regular variable in algebra. So we need to go through some definitions. We are going to take a little bit of time with this. So let me write them down, and then I promise I will make sure that everything is absolutely clear by examples. So here we have the idea of a random variable. Okay. In algebra, a variable is just something that can change or take on different values. Variable, the word variable means that it can change. But in statistics, a random variable is a variable whose value is determined by a random experiment. And when we say experiment in the context of statistics, I'm not talking about beakers and test tubes. I'm talking about you do something. Like an experiment might be drawing two cards from a deck of cards. What's the chances that I'm going to get two aces or two fours or whatever? There's a way to calculate that. Now, if I repeat that experiment with new decks, or maybe I shuffle the cards back into the deck to make a complete deck, I can do the experiment again. Well, did I get two fours that time? No. Okay, I can put it back in, do it again. Well, eventually I'm going to hit two fours. Eventually, if I do the experiment enough, if I have a deck of cards and I draw two cards at a time, eventually I'm going to get two fours. It may not be on the first try, may not be on the 10th try. It may take me 55 tries or 200 tries, but eventually it will happen. So when I say random variable, it doesn't really mean that it's randomized like a random number generator. It just means that the outcome of the experiment is basically going to be assigned to a variable. So the variable in this case could be, what do I get when I pull two cards from the deck? Well, the value of that variable, quote unquote, the value or the outcome of that variable is determined by a random experiment or some kind of statistical process. Could be flipping coins, could be pulling stuff from a deck of cards, could be observing population and asking a survey or something. It could be lots of different things. A random variable is just the outcome of an experiment, and you do the experiment a bunch of different times and you get a bunch of different outcomes. So the random part just means that you're doing it over and over again. You don't really know what's going to happen ahead of time, unlike in calculus or in algebra when you solve for a variable. The variable's always going to be, if you have a simple algebra equation, you can solve that equation, you get an answer. Answer might be 2, right? That's the variable you solve for the variable. That's the answer. But in statistics, the variable really depends on the experiment, and if I do the experiment 4 times, I might get different answers. Okay, now what I'm interested in statistics is what happens if I do the experiment 1,000 times. Can I draw conclusions? Is the random variable going to take on some values more likely than others if I do this experiment a lot of times? But anyway, the concept of the random variable is just I do an experiment, and then I do it again, and then I do it again, and then I do it again. Each time I get a result, usually I'm looking to see the specific outcome of something, and we're calling that a random variable because it might change each time I do the experiment. Now, I'll give you some more concrete examples in a minute. Let me show you what the idea of a discrete probability. For probability, I'll just do prob like that. And for distribution, I'll do dist like that. So this is discrete probability distribution. It is a table or a formula that lists the probabilities for each outcome of the random variable x. Now notice also the random variable we're calling x, usually in statistics, it's a capital X. Usually, you know, in algebra you have a little x, or you could use y or z in algebra. But in statistics, when it's a random variable, which just means it's an outcome of an experiment, that's all that a random variable is, you use a capital X, no curvy x's or anything like that. That's for algebra or calculus. In statistics, we use capital X, that means random variable. So don't worry about the word discrete, I will explain that in a minute, but the probability distribution, focus on that. It's a table or a formula that lists the probabilities for each outcome of the random variable x. So as we talked about with the idea of shuffling a deck of cards, we're going to get different outcomes when we draw two cards. We're going to get different outcomes. Now, sometimes we might get totally random things. Sometimes we might get a pair. We might get a pair, which means two cards of the same value, right? Now, there may be different probabilities associated with all those different outcomes, and the distribution of what those probabilities are is what we're talking about. It's called the probability distribution. Most of the time, it's represented as a table in terms of the discrete probability distribution here. I'll talk about the idea of a discrete in a second. So for a concrete example, I hate just, putting something on the screen, forever like this. What I want to do now is I want to give you a real example and show you what a probability distribution is. It's going to be much more concrete than a bunch of words like this. So for an example of a discrete probability distribution, let's flip 3 coins. So we're not just flipping a quarter, we're flipping 3 quarters at the same time. So we go flip, 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 and we observe the results, right? At same time. So then we will let random variable x be the number of heads showing. Okay, so that's our experiment. Then we're going to say, here is the discrete probability distribution of this experiment. So make sure you understand what's happening. I've got 3 quarters in my hand. This is the easiest way to do this, 3 quarters. I throw them up. They all go up at the same time. They all land on the ground. Sometimes I'm going to get all heads. Maybe I'm really lucky. I get all heads. Sometimes I'm going to get all tails. But most of the time, it's going to be a mixture of those two. I'm going to get some heads and some tails. Sometimes I'll get 1 head and 2 tails. Sometimes I will get 1 tail and 2 heads. Now, what we're trying to do is figure out all the different outcomes of this experiment, when I have 3 coins, all the different outcomes, and what is the likelihood of getting any of these different outcomes? The likelihood being the probability. That's what we kind of did a little probability refresher in the previous section. So the way to do this, a lot of times, especially in the beginning, is to draw a picture. Now, you can't do this with a lot of problems, but you can do it in the beginning to solidify. So when I do this experiment, I already said that sometimes, if I'm really lucky, I'm going to get 3 heads in a row. So let me just kind of write up here, this is 3 heads. Because notice the experiment says I flip 3 coins at the same time. Let the random variable x be the number of heads showing. The random variable that I care, which means the outcome of the experiment that I care about is just how many heads are showing. That's what I care about. So in this case, I write down, if this falls, I get 3 heads. But of course, I could have head, head, tail showing, in which case I only get 2 heads. Right? But I could also have heads, tail, heads, like this, which will also be 2 heads showing. Right? But then I can also have head, tail, tail, in which I only have 1 head showing. Right? And then I can have tail, head, head, and then I have, again, 2 heads showing. But then I can have tail, head, tail, which will only give me 1 head. And then I can have tail, tail, head, which is 1 head. And then I can have tail, 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 which is the other way I'm really lucky. Let's say 3 tails in a row, and I get 0 heads. All right. Effectively, this kind of is a raw representation of the outcome of the experiment. Now remember, the random variable I care about is how many heads. So for every single possible outcome, I have outlined every outcome that can possibly happen. No other outcomes can happen other than what I've written on the board. There's 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. And for every possible outcome, I have figured out what my random variable value would be, which means the outcome of the experiment, whatever I care about. Now notice that there's only one way in which I can get 3 heads. Only one way that can happen. There's also only one way that I can get 3 tails. So when you look at this, and if you're interested in the number of heads, then you can just tell by looking at this that the odds of getting 3 heads is lower than everything else. Because there's only one way on the board, one combination that gives me 3 heads. But if you look at the number 2, I get 2 heads here, 2 heads here, 2 heads here. So that's a little more likely to get 2 heads. Also, I get 1 head here, 1 head here, and 1 head here. That's also pretty likely because there's more ways in which that can happen. And then getting 0 heads is also pretty unlikely because there's only one way in which that can happen. So you can see that by flipping these 3 coins, and if I'm interested in the number of heads, sometimes you can just tell by looking at this, it's going to be more likely to get a mixture of heads and tails where I have 2 of one and 1 of the other. So this is sort of the raw information, but when we write the probability distribution, it says it's a table or a formula that lists the probabilities. I haven't listed any probability here because I just listed the raw outcome. If I want to write down the actual probability, then I might do something like this. So I'll do x. X means the outcome of the experiment. Notice this is like a cursive X. The outcome of the experiment can be 0 heads, 1 heads, 2 heads, or 3 heads. And I'll just remind you over here, I'll put heads. So I'm going to make a little table here, just like this. All right, this is a little table. Now, those are the possible outcomes of the experiment. So what would be the probability of my random variable capital X equaling lowercase x? This is a lot of the ways you'll see it written in a book. Basically, you're saying, what's the probability that I'm going to get a random variable equal to 0, a random variable equal to 1, random variable equal to 2, and a random variable equal to 3? We've written all this stuff down on the board, but we didn't write it in terms of probability. Remember I said, in terms of basic probability, the probability of an outcome is the number of ways in which I can get what I want, like when, flipping a coin, there's only 1 head, and there's 2 possible outcomes. Here, there are 8 possible outcomes. So if I want the probability of 0 heads, it's only one way in which that can happen, divided by 8 possible outcomes. So the probability of getting 0 heads is 1/8. And I can convert 1/8 to a decimal, just like, 0.5 or 0.3 or whatever, and I will get that. All right, what would be the probability of getting 1 head? Well, I get 1 head here, 1 head here, and 1 head here. So that's 3 ways in which I can get what I'm looking for, which is 1 head, out of 8 possible outcomes. So there's 3/8. Again, that's a number less than 1. That's a decimal, right? What's the probability of getting 2 heads? Well, I get 2 heads here, 2 heads here, and 2 heads here. Again, there's 3 possible ways to get that, and there's 8 possible ways in which my experiment can end. And then finally, what's the probability of getting 3 heads? I only have one way in which that can happen, and there's 8 possible outcomes. This is what we call a probability distribution, and furthermore, it's called a discrete probability distribution. I'll explain what that means in a minute, but basically on your exam or on your test or on your quiz, if the teacher gives you a problem like this and they say, create a probability distribution, this is what you're trying to write down. Some sort of table like this, where basically you want to list all the different outcomes and the probabilities that can be associated with those, and you can look at this in a glance. You could sort of see it from here, but you can look at this and really powerfully see that the probability of getting 1 head or 2 heads are equal. Right? The probabilities of getting 1 head or 2 heads are equal, even Steven, 3/8. Okay? The probability of getting 0 heads or 3 heads is also equal. That kind of makes intuitive sense as well. But it's a lower probability than this one. So I can look at this as a table, and I can look at all the different possible outcomes and see that they all have different probabilities. Of course, some of them are the same number, but basically there's a different probability in each column right there. So we're looking at the distribution or the spread of the probabilities among all the possible outcomes of this experiment. Now, what makes it discrete? What does the word discrete mean? And I'm not talking about when you tiptoe in the room and you're very discreet about it. I'm talking about in terms of math or geometry. Discrete means that something is finite. Something can only take on certain values. Those are discrete values. So, for instance, when you think about integers, those are discrete numbers. 1, 2, 3, 4. Those are the integers. 0, -1, -2. Those are also integers. They're just negative. So every whole number like that, negative plus positive, we call that an integer. Those are discrete numbers, okay? But when you start dealing with real numbers, with everyday life, you can have lots of numbers in between 0 and 1. In fact, there's infinite numbers just between 0 and 1. There's infinite numbers. Just between 3 and 4, there's infinite numbers because you could have 3.45678 10, whatever. You can have infinite decimal points to split up everything between an integer pair on the number line, right? So that would be called continuous. When you look at continuous values, you have a problem where you can take on values that really can have any number of decimal points. That would be continuous. But this is not continuous because the outcome of the experiment can only have certain values. You can only get 0 or 1 or 2 or 3 heads. You can't get 2.5 heads or 3.25 heads in this experiment. You can't. It just physically, you're throwing coins and you look at the results. So because of that, you're only going to have 1, 2, 3, 4 columns, and so you can only have 4 probabilities. You can't have anything more or less than that. So this is called a discrete probability distribution. When you have values where you can write it down in terms of a table and capture everything, and that's all you can get, that's called discrete. And let me jump ahead just a little bit and tell you that most of the time in statistics, we're not going to be dealing with discrete probability distributions. We're doing this to mostly show you the idea behind what a distribution is. But in real life, what if I wanted to look at the probability of someone having a certain height? Or what if I took a survey and looked at everybody in the world and looked at their height, right? And I tried to figure out what would be the probability distribution of getting different heights of people, right? Well, some people are going to be 4 feet tall, it's some short. Some people are going to be 7 feet tall, that's real tall. And some people may even be taller or shorter than that, right? Some people may be in the middle, more like 5 or 6 feet tall. But there's always going to be people that are not exactly 6 feet tall. They may be 6.125 feet tall. There's always going to be people that are 5.795 feet tall. In other words, if you look at somebody and try to figure out the distribution of world heights, there's going to be basically almost infinite values in between because height is something that's not discrete. Height is continuous. You might have somebody that's 4 feet, 5 feet, 4.5 feet, 4.75 feet, 4.8 feet. There's many, many different values that height can take. So when you look at the real world and you're trying to take surveys of people's height and do problems with the probability of certain height distributions in the country, or the length of people's finger, there's going to be infinite number of answers there. And so it's not discrete whenever you're talking about real world problems a lot of times. That's the bottom line. So as we go forward, we're going to be continuing to talk about the probability distribution concept, but they won't be discrete. They'll be what we call continuous. And we'll get to that a little bit later. But for now, just remember this is a discrete probability distribution. There's one thing I want to point out to you that's extremely important. Okay? Here we said the probability of our random variable having 0 heads is 1/8. Probability of getting 1 head is 3/8. Probability of 2 heads is 3/8. Probability of 3 heads is again 1/8. Let me show you something. What is 1/8 plus 3/8 plus 3/8 plus 1/8? Well, you have to bust out your fraction math. Notice that all of the denominators are 8, so that's convenient. So all we do is we put an 8 on the bottom, and we add fractions if the denominator is the same. 1 plus 3 is 4. 4 plus 3 is 7. 7 plus 1 is 8. So we get 8 over 8, and that equals 1. When we do fractions, 8 divided by 8 gives you 1. So what I'm trying to say is the sum, this is extremely important actually, the sum of all of the probabilities in our distribution equal 1. Let me say that again. The sum of all of our probabilities in our distribution equal 1. That's very, very important. That means that if I do this experiment, I'm always going to get one of these results. That's what it basically means. If I'm looking at the probability of this or this happening or this happening or this happening, I add them all together, I'm guaranteed to cover every possible outcome because these are all the outcomes that will happen. So when I throw 3 coins and I get a result, I'm guaranteed to get one of these because the sum of all of the probabilities of all the outcomes is 1, which means 100% chance of happening, all right, like 100% chance of rain. So that's going to be true of all distributions, all probability distributions. I should be able to look at the probabilities and sum them all up, and they should always equal 1 because I'm trying to cover all possible outcomes of the experiment to guarantee that it will happen. All right, let's do another one real quick. We're not going to beat it into quite as much detail, but I think it's a very good problem, so I want to do it for you. So what would be the probability distribution for the random variable x, that's capital X, notice, which would be the sum of 2 rolled dice, right? 2 rolled dice. And so when I'm talking about dice is I'm saying one die has 6 faces. So we can get 1, 2, 3, 4, 5, 6 off of one die. And then I roll a second die, I can get 1, 2, 3, 4, 5, or 6 off of the second die. So when I roll a pair like that and I add the 2 together, so I'm saying the sum of the 2 rolled dice, sometimes I roll 2 1s and I'll get an answer of 2. Sometimes I roll 2 6s and I get an answer of 12. But much more commonly I'll get other combinations and I'll get the sum. I'm trying to figure out what's the probability distribution of getting different sums whenever I roll dice. So if I wanted to do that, I would create a probability distribution. I'll try to squeeze it in here. It's a lot of answers, but basically I would say the probability of my random variable capital X being equal to all the possible values that I have here. What are the possible values that I can take? Well, if I roll a pair of dice, I can never get a 1 as a sum because I'm always going to have 2 die and I'm always going to have at least 1 on each. So you can never get a sum of 1, but you can get a sum of 2, right? So I can get a sum of 2. I can also get a sum of 3. I can get a sum of 4, 5, 6, 7, 8, 9, 10, 11, and 12. The maximum sum I can get is 12 if I roll 6 and 6. So the sum of all of the different ways in which I can get, if I roll 2 dice, is really going to be one of these answers. I can never get a 1 and I can never get a 13 or higher. So let me draw this like this. And let me make this into like a little table because remember our discrete probability distribution should look like a table almost all of the time. All right, so let's go and look at this here. Let's just take a couple we're not going to work out the answer for every one, but let's look at a couple. Let's look at the number 2. How can I get the number 2, right? The only way in which I can get a number 2 is to get a 1 on one dice plus a 1 on another dice, right? I can get a 1 plus 1. If this ended up being 1 plus 2, then it wouldn't add right. So the only way in which you can get 2 is 1 and 1. So as far as combinations go, there's only one way in which I can get this guy to add up, and there's 36 different combinations of the ways in which the dice can roll. The reason there's 36 of them is because there's 6 faces on one die and 6 faces on another die. 6 times 6 means there's 36 ways in which the 2 dice can land. All right, 36 different possible outcomes in which they can land. Only one of those outcomes will yield a sum of 2. Okay. Similarly, look way over here. When you look at the number 12, the only way I can get that is 6 plus 6. There's no other way I can add to 12 because the dies only go up to 6. All right? So there's only one possible outcome here to give me a 12, but there's 36 possible ways in which the die can be rolled. And then we'll just do this one as sort of a last one. If you look at the number 3, how can I get the number 3? How can I get the number 3? Well, one die I can get 1 plus 2. Okay, and the other die I can get 2 plus 1. Those are the only ways in which I can roll this pair of dice to get the sum of 3. That's the only ways in which it can happen. I can get a 1 on dice A and a 2 on dice B, or a 2 on dice A and a 1 on dice B. So there's only 2 possible ways I can sum to 3, again out of 36. Again out of 36. So you can see what you end up having to do through here. I would have to go look at the number 4, and I'd have to go figure out, okay, how can I get the number 4 to be summed together? And you'll find that there's only 3 ways in which to sum to number 4, 36. In fact, I can just show you real quick. How can we get to the number 4? Well, we can do 1 plus 3, we can do 3 plus 1, or we could do 2 plus 2. Those are the only ways in which I can add to the number 4. So there's 3 outcomes that yield a sum of 4. There's 36 possible outcomes. So I'll just fill in the rest of the chart. For the number 5, there's 4 ways in which that can happen out of 36 outcomes. This one is 5 ways in which it can happen. This one here is 6 ways in which it can happen. The number 8, there's 5 ways in which it can happen. The number 9, there's 4 ways in which it can happen. The number 10 is 3 ways in which it can happen. And the number 11 is 2 ways in which it can happen. This one's pretty easy to understand, 11. The only way I can add to 11 is 5 plus 6 or 6 plus 5. There's only 2 ways in which that can happen, so there's 2 outcomes. Notice the denominator is always 36 because when we're doing probability, we're trying to say how many ways in which my outcome can happen divided by, or with fraction bar, over how many possible outcomes are there. There's always 36 outcomes. So now I can look at this. This is a discrete probability distribution. This would be the answer. The reason it's discrete is because my experiment can only end by getting one of these answers. It can only sum to 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. It can't sum to anything else, and you can never have values between 7 and 8 or between 10 and 11 that could be valid outcomes. You just can't, because this is a discrete experiment with a discrete outcome, as opposed to continuous outcomes like we discussed earlier with heights of people and things like that. We'll get to those a little bit later. So this would be the answer, and again, I think I showed you over here when we talked about this probability distribution, I said the sum of these always have to add to be equal to 1. Well, the sum of these should always add to be 1 as well. And if you think about it, all I would have to do is add all of these together. So if I wanted to add, I could say, well, the sum is going to be equal to something over 36 because 36 is the common denominator. So then I have to add 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. I promise you, if you add that together, you will get 36, which will equal 1. That means the sum of all of the outcomes of the experiment have to give you a 100% chance of happening. So if I do this experiment, I'm covered by every single possible outcome, because there's no other outcomes there, and so if I add them all together, I should be covered by all of them. There's one final thing I'll show you here. We're getting the probability of each possible outcome of our random variable. We're also showing that we sum all of these things together, and we're covered because the outcome of all of those sums is 1, or 100%. The other thing is, and we'll get to this a little bit later, if I asked you, what would be the probability that the sum of the dice that are rolled is less than or equal to 3, okay? If I asked you that, if I said, normally when I'm asking you a question on a table like this, I'm saying, hey, what's the probability of getting a 7 when you sum them together and you get a 7? What's the probability of getting a 10 if you sum them together? What's the probability of getting a 12 if you sum them together? But I can also ask things like, hey, what's the probability of getting a sum less than or equal to 9? Or a sum less than or equal to 5? Let's say, if I wanted to ask you, what's the sum, or what's the probability of getting a sum less than or equal to 3? That would mean it would be okay if I get a 3 as a sum or a 2 as a sum. So I could say the probability of getting less than or equal to 3 would be the probability of this plus the probability of this, which would be 336, 3 over 36. I would just add the probabilities together. So if I wanted to say, hey, what's the probability of getting a 6 or fewer, or a 6 or lower sum, then it would be here all the way down. I would just add all of these probabilities together. So looking at a table like this, you can look at individual outcomes and see the probability. You can also quickly calculate the probability of getting less than something or greater than something just by summing the probabilities of the outcomes together. And we're going to do a little bit more of that later. This has turned into a lengthy lesson. I'm going to stop it here. We've covered everything we wanted to cover, but it's so important because the rest of the course is really going to be built upon doing probability distributions and understanding different kinds of distributions, and we'll see as we get a little bit farther the details involved in that, but basically you have to understand backwards and forwards what a probability distribution is. And I hope I've explained that here with a couple of examples. So this knowledge and this kind of mental image that you built of what a distribution is of probabilities will carry on as we do all of the different kinds of problems forward. So kind of ingrain this in your head, make sure you understand these concepts. Follow me on to the next lesson where we will continue working with statistics and distributions and using those concepts to calculate useful quantities in statistics.